and so on. And I will add a few things also, which have not been addressed in previous lectures.
There was not so many talks about
Okay.
EN, I would say. Not
In
so
any
you
case,
should not maybe go to...
I will start with recollections about little disk. Okay, let's start. So briefly, the operads of little n disk was introduced in topology, so in the late 60s by Portman-Vogt. And this operad was introduced in order to model structures which are attached to n-fold loop spaces. So I will quickly recall this motivation, for this is not the main focus of my talk. And I will also recall the works of these people, Portman-Vogt and Peter May, which is the recognition theorem which says that n-fold loop spaces can be recognized by some kind of multiplicative structure which is encoded by operads, by these operads actually. Okay. And I would like to say that little disk operads are also used to define a hierarchy of homotopy commutative structures. So this starts with homotopy associative but non-commutative. So there is an index here n. So this starts with n equals 1, where you get a structure which is fully homotopy associative but not commutative at all. And the hierarchy goes up to fully homotopy associative and commutative, and this is for n equals infinity. And you have a range of intermediate structures which are in some sense commutative up to some degree only. Okay. And so you have this little disk model, but in homotopic algebra, it's often one has to change the model. I mean, this is not, so this is one particular operad, but if you want to construct an operad action, then it might be better to change this operad to another one. That's why people introduce the notion of an EN operad. And I will explain the precise definition of this notion, just say that this is something, these are operads in topological spaces. You can also define operads in chain complexes and so on, which are weakly equivalent, so in some sense, or homotopy equivalent, you can say for a moment, to this little disk model. Okay. So the plan of my talk is the following. So I'll first recall this little disk and little cube picture, and then I will introduce another example, which is my favorite operad, which is the Barrett-Eccles operad. Okay, and I will go back to the surjection operad, which was introduced by John in his lectures, in his lecture series. And I would like to explain that there is some kind of geometric picture which says that this surjection operad arises from some kind of prismatic decomposition from this operad in simplicial sets. And then finally, at the end of this hour, I will explain some motivation, some statement which is a Koszul duality result for EN operad. So I think that Bruno has already spoken about the Koszul duality of the Gershner operad. And there is something at the chain level which realizes this Koszul duality equivalence. And then, so I will conclude with some miscellaneous models. I will say, I don't pretend I will be comprehensive at this stage, so probably some people will be upset not to see their favorite model of EN operads occurring in this talk, but, but I can't do otherwise. Okay, so let's start with this little disk picture. Okay, so that's the best thing is to give a picture of this little disk operad. So first, the little disk spaces. So the operad is a collection of spaces, which I denote by dnr. So the n stands for the dimension. So in this picture on the blackboard, the dimension is 2. Okay, and this little n r is the operadic arity. And so this space, dn of r, consists of collections of r little n disk with disjoint interior inside a fixed unique n disk. So you see, for instance, in this picture, so this is an element in D24, so this is a configuration of 4 little disks which are embedded in this, so the unit disk is materialized by this light gray picture. Okay, and the little disks are numbered from 1 up to the arity. So in this case 4, from 1 to 4. Okay, so and so yeah, I would like to say, so first thing, that if you regard this object as a space, then it's obviously homotopy equivalent to the configuration space of points, of all distinct points in the open-end disk. So this is the picture of a point in this configuration space. So in RET4, it consists of 4 distinct points. And the homotopic event, which goes from this space to this one, is just the map which maps each little disk to its center. Okay, so for instance, this little disk is mapped to this center Z1, this one to Z2, this one to Z3, and the center of this one is this cross Z4. Okay, and you can define a map the other way around, and you can easily check that these maps are homotopy. That this map is a homotopic event. Okay, so very easy to define a homotopy. Okay, yeah, so that's the claim. There's a homotopic event. Okay. So, but there is one structure which the little disk have. So there is first structure, you have an action of a symmetric group. For instance, if I go back to this picture, if I would like to consider the action of the permutation, so let's say 1, the permutation which takes 1, 2, 3, 4 to 2, 3, 4, 1. If you want to take the action of this permutation of this little disk, then you just change the indices of this little disk. So this 1 is mapped to 2, 2 is mapped to 3, 3 to 4, and 4 to 1. Okay, and you have also an obvious. So you have also an obvious action on this space. Yeah. So, yeah. So you see that this map, this space inherits an obvious action of a symmetric group 2, and this map is actually an equivariant homotopic event. Okay, but you have more. I mean, you have also in the little disk space this kind of composition which define an operad structure on these spaces. And these maps are defined by an obvious substitution process. So I've represented an example here. So I'm taking the composite of this configuration at the second position on this one. So this just means that I insert this little disk configuration on the little disk marked by 2 in this configuration. And I get this picture. So I get a configuration of 4 little disks. And of course, I have to renumber, to reindex. I have to shift the index of this little disk in order to get disk numbered from 1 to 4. Okay? So, and the little disk operad is just a whole object defined by this collection of spaces and these symmetric structures and this composition operation which are defined for all R, S, and K. Okay. So this is one example of an operad. There is another basic example which is the little cubes operad. So it just means that you replace disk by cubes. So the little n cubes operad is a collection of spaces, C and R, which are defined just as the little n disk spaces, except that you consider this kind of configuration of little cubes in a big unit cube. Okay, so this example, this element is a
cube. How is it a cube?
So yeah, cubes mean rectangles. So actually, you allow. Yeah. Okay. You allow. So the only significant thing you see is that the boundaries of the rectangles are parallel to the boundaries of a unit cube. Okay. So you are looking at some kind of specific, some kind of particular embeddings from this cube to this one. So I mean embeddings which consist of a change of scales in different directions followed by a translation. Okay? And so this is elements in the space C2, 4, configuration of 4.
Excuse me. Regarding your example in previous slide,
Yeah.
when you had the one more, yeah, here you have the composition for the disk opera. Do you have also for configuration spaces?
No. That's the main point. So on little d spaces, you have this kind of composition operation that you cannot define at the level of configuration spaces. You have only some kind of composition, on configuration spaces, you have only an action of a symmetry group and some kind of removal operations. You can also consider a composition with an empty collection, and that this just amounts to removing this little disk. This is the only kind of composition operation that you get on configuration spaces. So that's the main advantage of the little disk. And yeah, so the little cube spaces are defined similarly. So I'm considering this kind of rectilinear embeddings of cubes. Okay, so this gives a configuration of 4 cubes in a big unit cubes, which are again numbered from 1 to 4. And again, I'm assuming that the interiors of the cubes are disjoints. I mean, the cubes can touch on the boundary, and the boundary of the little cubes can touch the boundary of a big ambient cube. Okay? And so, and you have also symmetric and composition structures on this operads which are defined as in the little disk setting. So these are 2 similar operads.
So the cubes have to be straight.
Yeah, exactly. You have boundaries of the cubes have to be parallel to the boundaries of an ambient cube. So that's the point. Okay, and you have also an equivalence or amount of equivalence between this space and between each little cube space and the space of configuration of points in the interior of a big ambient cube. Okay, okay. So these are 2 models. So one. And so the little disk model has some advantage because you can add more structure. You can rotate cubes. You can define frame version of little disk, things that you can do with cubes. But the little cubes is better if you try to look at the action of operads on iterated loop spaces. So because it's easier so I mean, I will go to this subject in the next slide and I will explain. So in that case, I'm dealing with little cubes rather than little disk model. Okay, so first reminder. So I've said that the little n cubes operad and the little disk operad, similarly, encodes operations acting on iterated loop spaces. So maybe I will draw the picture. So omega n x. So x is a base space. And omega n x is the set of maps from the n-dimensional sphere to x, set of maps preserving the base point. So it's a space, actually. It's a topological space. And so to get the action, what I consider, I can regard the cubical model of Sn. So this means that I can look at the model of Sn, which is the n cubes mod its boundary, 2x. Okay. So, and Cn, the little cube space, acts on omega n x. So this means that each little cube's element, each little cube's configuration, gives rise to a map, gives rise to an operation. I will denote by C bar again. So this is an operation which associates any R tuple of element in omega n to another element in omega n. And if I consider the picture of this C bar, okay, so C bar is a configuration of cubes. This one, and so each alpha I is a map from the cube modulo the boundary to x. To get this composite map, what you do is you map these little cubes into x by using alpha 1. this little cubes to x by using alpha 2, and this little cube to x by using alpha 3. And the points which are not in the little disk, in the little cube, sorry, are mapped to the trivial element, to the base point. And so that way, from 3 maps from Sn to x, you get another map from Sn to x. Okay? And so this is perfectly continuous. Okay? The main point, the main statement, so you have 2 statements. We have one which is the May's approximation theorem. So now I need to explain what is this sigma n. So sigma n of x is the suspension. So it's the sphere cross x, and you divide, you take the base point of the sphere times x, and the Sn cross the base point of x to the base point. You collapse this, you collapse this set to a single point. Okay, so this is the suspension, and the May's approximation theorem says that if you form some kind of free algebra over the little cube operad generated by x, then you get a model for omega n sigma n x, the n-fold loop space on the n-fold suspension of x, of the space x. Okay, so it's a comparison between between a paradic algebra structure and some kind of topological construction. Okay, so the approximation theorem says that this map is a weak occurrence, provided that X is connected, or more generally group-like. So group-like means that if you take the, oops, no, it's a mistake. It's a typo. This doesn't make sense here. So group-like is in the next theorem. Yeah. In general, what you get is that this map is a group completion. So, but to be simple, let's say that if X is group-like, then you get that this map is a weak occurrence of spaces. So this is my notation for the free Cn algebra. Okay, I'm adding a star, which means that I identify. So there is some kind of additional identity, which makes the base point of X a unit for this Cn algebra structure. I will explain that with more details later on, when I go back to, when I come to more combinatorial models of this object. Okay, so next statement is the recognition theorem, which now says that if y is connected, or more generally group-like, and if y is equipped with an action of this operad of little cubes, then y is actually an n-fold loop space for some delooping, so X is usually called the delooping. Okay. So this says exactly that you can read this kind of topological construction. You have an algebraic structure which allows you to reconstruct this topological object. Okay. So, and I should say that this theorem works for n going from 1 to infinity, but I have to explain what is C infinity and D infinity. Okay, so okay, so that's the main motivation for the introduction of little cubes. Maybe I should say the difference, one advantage of little disk over little cubes in this approximation theorem here. What you can do, you have a map, so in topology, just briefly, you have a natural map from sigma omega n sigma n x to omega n minus 1 sigma n x. So this map comes from an adjunction between the loop space and the suspension construction. And this map has actually a model at the level of this free algebra of the little cubes operad. You have something which is Cn. So you have this equivalence coming from the May approximation theorem. You have another equivalence here. and this stabilization map has a counterpart at the level of free algebra over little n cubes, over little cubes. Okay. So this is the main reason why little cube operad may be better for the study of iterative loop spaces. Okay, so I have two, but I should say I have two operads. So now, so that's the original motivation for the introduction of little n disks and little n cubes. Now I'd like to explain what an EN operad is.
Sorry, the suspension on the left, the suspension of S lower star, is just the shift.
No. It's so it's this kind of construction. The
No,
suspension.
but not this one. The one.
Where?
Bottom one. Yeah.
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 No.
Is it short?
The star doesn't refer to a degree. It's a topological
No,
object.
but this is an algebra.
This is
It's not.
just a suspension of
Yeah,
this
it's real
object as a
suspension
space.
as a topological space.
So yeah, in this for the moment, algebra means topological space. Algebra in topological space. Some kind.
Your S star is not singular chains, is it?
No. Yeah.
Yeah.
Yeah. It's so in my notation, it's you see it's a true type font. So okay. Okay. Yeah. So this is just a notation for free algebra. Maybe in other talks it was denoted by Cn of x, but then I have to add this star condition. So I'll come back to this point later on. Okay. Yeah, this S refers to the fact that this is some kind of generalized symmetric algebra. Okay, and star refers to the identity for the base point. Okay, so. Okay, now I would like to give a definition of an EN operad. So we have a natural notion of recurrence of operads in topological spaces. So I have not recalled the definition of an operad morphism, but you imagine what it is. So it's just a collection of maps that intertwines the structures attached to operads. Okay, and so I will say that such an operad morphism is a weak occurrence of operads if each component of this morphism is a weak occurrence of topological space. So, okay. So this is a definition which makes sense in every context where you have a notion of weak occurrence. So in the simplest case in the topological setting, but you can also define weak occurrences of operads in chain complexes and so on. Okay. So each time, so some people say that weak occurrences are defined, are created arity-wise in the base category. Okay? So this is the obvious definition. And I will use this notation to mark any distinguished class of weak occurrences in a category. Okay, so this is the standard notation in topology. So I will say that an operad in topological spaces, En, is an En operad if this operad, En, is connected to the operad of little n disk by a chain of operad morphisms of this form, so where each morphism is an operad weak occurrence. Okay, so the intermediate objects have to be operads, and the morphisms have the weak occurrences have to intertwine the operad structures. So there's an exercise which is very nice but not so easy. I claim that the little n disk and the little n cubes operad are connected by such a chain of operad weak occurrences. Okay. So if you remember, I've said that the little n disk space, each little n disk space is homotopy equivalent to the configuration space of R points in the n-dimensional disk. Okay, and you have a similar weak occurrence between the space of little n cubes and the configured space of R points in the n-dimensional little cubes, in the n-dimensional cubes. Okay. So the spaces are homeomorphic. So you clearly have homomorphism at this level too. Okay, so this gives a chain of recurrences of spaces connected the little cube spaces and the little d spaces. And the claim is that this chain can be upgraded to a chain of morphisms, which are still recurrences and which intertwine the operatic composition structures. Okay? It's not so easy, because you cannot do that by saying, so I'm starting with a little cubes, with a little disk configuration. I'm taking the largest cubes inside the little disk and check that it works, because it doesn't work. This map doesn't preserve the operatic composition structures. So it's
I think you said before that the configuration of points.
They are not open.
no, they are not operads, okay?
But you have to replace them, yeah?
Okay, yeah, exactly. So the claim is that you can upgrade.
Okay.
The claim is that this chain, this collection of chains of recurrences of spaces can be upgraded to a chain of recurrences of operads. Around. So this means that the middle term has to be an operad too. Okay. So in principle, you can do that by using the Boardman-Fogg construction. Okay. To construct such a chain by hand, I don't know if this is possible actually. I'll try to do the exercise by hand. So this the problem. So you see.
Look, can I ask my question here? What would happen if you replace the little discs opera by the Fulton-McPherson opera?
Yeah, in that case, so the Fulton-McPherson is cofibrant. In that case, you can there is no need to consider chains like that.
Yes.
In the Fulton-McPherson case, you can just consider one map going one direction map.
Yes.
Okay.
Does that make it easier, or is it?
Yeah. Yeah. In that case, it's much. You can work out this exercise by using the Fulton-McPherson opera.
I just wonder why then don't you take the Fulton-McPherson opera as the standard model for the EN opera?
Because the little disk model is easier. My standard model is the Barra-Teicholz opera in any case, so it's for some reasons. Fulton-McPherson is obtained by some kind of compactification of this configuration space.
Yeah, now I understand the since these are not operas.
These are not operas.
You make it into operas by compactifying.
Well,
It's just the Fulton-McPherson compactification is, as a set, the free opera generated by the space you started off with.
exactly.
Oh, it's true that you can plug a stable configuration into a stable configuration.
Yeah, exactly.
Yeah, that's clear.
Yeah.
That's exactly what
Yeah.
Okay. So actually each opera has its advantage. So it's So in any case, so this result says that the little disk model and the little cubes model give the same notion of an opera. So the actual problem, so in many applications, you have an opera and you want to prove that this opera is EN. This means that it is related to DN by such a chain. And this is actually usually the hard point of applications. So the basic problem is how to recognize the operas. And maybe I will add another problem. So if you can construct such a chain of recurrences, how many chains do you have? And the answer is, in some cases, is the Grothendieck-Teichmüller group. And this is what I'm going to explain in the second talk today. Okay. So we would like to have some kind of machine which enables you to reconstruct such a chain of recurrences from internal structures of our part. And this is what I'm going to explain actually with the Barra-Teicholz model in the second part of this talk. Okay. So I will add a few things about this little disk. So one is what I call the equatorial embedding. So this says that, so I claim that so here this is the space of little n-1 disk. This is the space of little n disk inside the big unit n disk. And there is maybe that's better to give a picture. Okay. So this is the space. This is a point. This is the configuration in the space of little one disk. And there is a map which to this configuration assigns the configuration of little 2 disk with the same centers on the equatorial hyperplane. Okay, so this I'm fixing the center. Maybe that's better if I draw it. So I take the same center. So you see the center is here. So I keep the center. I take the same center on the axis. Okay. And I keep the same radius. So you see. Oops. Ah. Okay. So, okay. So here I keep the radius too. Okay. And that way. Okay. And that way I get an operad maps. And actually it's a topological inclusion, which means that dn-1 is so the spaces can really be identified with subspaces of D and R. Okay. And you can easily check that this topological inclusion preserves the operatic structures, the symmetric structures and the composition structures. Okay. So from this construction, I deduce that the little disk operad form a nested sequence of operads in topological spaces. Okay. And this gives a sense to this hierarchy of homotopy commutative structures. I will say a little more. So for a moment, I've only defined dn for n finite. And I can also take the colimit of this sequence to get an infinite dimensional version of a little n disk of a little disk opera. Okay. And you can identify these external terms. So this is the following proposition. So if you look at this space D1R, okay, the space of little intervals, then this space is homotopy equivalent to the symmetric group. So in this homotopy equivalence, I regard the symmetric group as a discrete set, as a discrete topological space. Okay, and the homotopy equivalences of spaces, which gives this connection, they carry the structure of this operad to the structure of the operad of associative monoids, as. Okay, so I think this operad has been introduced earlier. So as R is the operad of associative monoids. So maybe Bruno has talked about this operad in the module setting. So in the set setting, I'm just taking the components of a operad of symmetric groups. Then you have an operadic composition of permutations. So for instance, 1, 2, permutation 1, 2 compose at position 2 with 2, 1. With compose at position 1. This means that you replace this one by this sequence, and you shift the remaining term of the permutation. Okay? And so this is an operad that governs associative monoids. And I claim that actually D1, the operad of little one disk, is equivalent to this operad. Okay? So this explains that algebras about D1 are nothing but strongly homotopy associative monoids. Monoids which are homotopy associative in the strongest sense. Okay? And if you look at the limit term, the colimit, D infinity, then you can see that these spaces are contractible. Each space, D infinity, is homotopy equivalent to a point. And this implies that this operad, D infinity, is equivalent as an operad to the operad of associative and commutative monoids, COM. Okay, so COM is the set context. So just the operad which has the 1-point set in each arity. Okay, with the obvious operatic structure. Okay, and so this gives you a very easy criterion to recognize E1 operad. So to check that an operad is E1, you just have to check that it is equivalent to the associative operad as an operad in sets, as an operad in topological spaces. Okay, so you just have to check that the homotopy, the path-connected components of this operad are contractible, and you have sigma R path-connected components, and you have to check that the composition of path-connected components corresponds to the composition in the symmetric group. Okay. In that case, this is still easier. You just have to check that the operad is contractible to get that this operad is E infinity. Okay. So it's in the intermediate case that's more difficult. Okay. Maybe what I would like to do to conclude this section is to recall the computation of the homology of Dn. Okay. So this is a theorem of Fred-Cohen, which says that I'm assuming that for n equals 1, we know the answer. The D1 is the associative operad, so discrete objects. So the homology is just the associative operad. So let's assume that n is larger than 1 and finite. In this case, so the homology of Dn, the homology of this operad can be described by generators and relations. It's actually identified with an object which I call the nth Gershnaber operad. So maybe there is a change of notation. In John's talk, it was my Gersh n was denoted by Gn minus 1, maybe. Okay, so okay. So here this n refers to the dimensions of the cubes or of the disk, and this n minus 1 refers to the degrees of the generating operation. So you have two generating operations, one which is the cup product, so it's an operation in RT2, it has degree 0, and it is symmetric. Another one, which is the broader bracket or the Lie bracket, which is again in RT2, which has degree n minus 1, and this operation is symmetric or antisymmetric depending on the parity of n. Okay? And maybe just to explain this statement, so the definition of these operations. You can deduce the definition of this operation from this homotopy equivalence between Dn2 in the configuration space of 2 points in Dn. And you can see that this configuration space is homotopy equivalent to the n-1 dimensional sphere. Okay, so this implies that the homology of Dn2, basically you have, it's one line in degree 0, one line in degree n-1, and 0 otherwise. Okay. And so so this mu is the fundamental class of the point, and this lambda is the fundamental class of the n-1 dimensional sphere. Okay, so this n-1 here was referring to this dimension. Okay, and you have generating relations. I'm not going to recall this relation. You have the associativity relation for mu, the Jacobi relation for lambda, and the Poisson distribution relation between mu and lambda. Okay, so. And I would like to add a point about units. So I'm not going to be very explicit about unit problems. So I have to say that there is also an operation in RET0 which gives a unit for this product and a unit for a bracket. So unit for the bracket means that it is central with respect to the bracket. Okay, and so that's for technical reason. I'm not putting this unitary operation in the generating operation of the operad. I regard the unit as something which is added to the operad, and which gives some kind of extension of the symmetric structure of the operad. So it's And actually, this construction of the free algebra where base point is identified to units is related to this convention. Okay. So, yes. So from this statement, already from this assertion, you immediately see that this operad is not contractible. So it's not so easy to determine this operad. There is a problem of which I don't know the answer. I mean, how many topological operads do you have with this homology? How many topological operads have the Gaussian number of operads as homology? I don't know. The problem is to classify or to determine the moduli space of operads of topological spaces of which homology is the Gaussian number of operads. Okay. So this is related to an obstruction Fourier approach to the so at least in the case n equals 2, to an obstruction Fourier approach to the definition of associators and of a Grothendieck-Teichmüller group. Okay. And so I can, to complete this statement, I can describe the map, so the equatorial embedding, the map induced by the equatorial embedding. Okay. And you can determine this map on generating operation, and obviously, so it's in reality 2, it's induced by something which goes from the sphere of dimension n-2 to the sphere on dimension n-1, and it is the identity in degree 0 and trivial in degree larger than 0. Okay. Okay. So this is the little disk picture. Now I'm moving to a Barre-Teckels operad. Okay. So yeah, and I will also explain together with the Barre-Teckels operads this kind of recognition methods and one which is due to Clemens Berger. Okay. So I mean, maybe I will recall. So I explain this statement. So I explained that in the case n equals 1. You have a weak equivalence between the operad of little intervals, the operad of little one disk, and the operad of associative monoids. And this equivalence implies that the free algebra over the little one disk operad, which is a model for omega sigma x, the one-fold loop space on the one-fold suspension of x, this free algebra is weak equivalent as a collection of spaces to this free algebra over the operad as. So this is nothing but the free associative monoid. And this is a classical construction of topology. This is a construction of Johann James. So it's a free associative monoid generated by x. And you divide by the relation that the base point of x has to give a unit of this monoid. Okay, so it's some kind of, so you add this quotient to this kind of tensor algebra in spaces. Okay, and actually the equivalent between this construction and this one is a flower of James, actually. Maybe it dates from the 50s or something like that. Okay.
Sorry, if you've never seen that. For instance, if x is a circle.
If x is a circle.
What does it look like? You can't. It's nothing special.
Nothing special. You can.
Just the next example after the point.
What you can do if x is the case of a circle, you can actually split this construction, and that you get a nice picture. Otherwise, you can't say more than saying that it is the free associative monoid generated by x. So what you can do is, so it's a quotient that you can split. Maybe I should mention that there is a splitting theorem. Say that at least stably this is a wedge of smash powers of x. Okay, if you stabilize in the stable homotopy world, then you really retrieve some kind of tensor algebra. Okay, so if you take that, if x is S1, then you get here SR, the half-dimensional sphere. So it gives some kind of approach to analyze this construction. Okay. 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 Yeah. Okay. And yeah, for n equals infinity.
Excuse me. Free associative monoid generated by x is equal to the disjoint union products of x.
Yeah, but yeah, okay. Maybe I will write down the explicit construction. I take this disjoint union, So the free associative monoid generated by X, I take this disjoint union, okay, where R ranges from 0 to infinity of a Cartesian power of copies of X. But now I divide by a relation which says that the base point of X has to be a unit in S star. Okay? So that's why you get such a splitting only stably.
So this will be the wedge of the smash products?
Yeah,
No, I mean,
this is the
after quotient.
after a quotient here. Yeah, no, it's
But it's filtered. So
it's
the
filtered.
associative-
So in that case, you can control the stability of the splitting. Actually, that's, you can only control from one subpart of a free monoid.
For instance, point, cross point is
Yeah, exactly.
Right,
You have that.
for example.
X1, if you have a base point at position R, then you want that this to be equal to the same thing with this base point removed. Okay. Thank you. So this is for n equals 1. So this gives a nice combinatorial model of this object. And for n equals infinity, we cannot do that with a free commutative model. So you can actually compute this, the homology of omega infinity, sigma infinity, and the homology of the free symmetric algebra. So it's a classical computation by Doll. And you see that you don't get the same thing. And the reason, okay, that this construction preserves only recurrences between operads where you have a nice enough action of a symmetry group. So I'm not precise at this stage. I should say that. So if you assume that your operad consists of cell complexes and the symmetry group permute cells, then this is okay. So the main notion is to have a sigma cofibrillant operad. Okay. So the motivation of Barra-Teckles was to give such a kind of combinatorial construction by replacing the commutative by another operad, which I denote by W, which is a kind of sigma cofibrillant replacement of the commutative operad. So and this is a very basic object. Actually, this is just the homogeneous bar construction of a symmetry group, and I'm going to recall the explicit definition. So it's an operad in simplicial sets, actually. Afterwards, I will take the topological organization of this operad. For the moment, I'll give the definition of each WR in the category of simplicial sets. So the simplicial sets, so the set of d-dimensional simplices of this simplicial set is a set of d+1 tuples where W0, WD are permutations of one R. Okay? And the faces are given by a usual map which remove the I plus 1 component of such a d+1 tuple, and the degeneracies are given by the repetition of components. Okay? So the symmetry group acts diagonally on WR, and you have also operadic composition operations which are defined factorized by this operadic composition of permutations. So this means that if you factorize, means that if you take, so it's a map of simplicial set. This is supposed to take a simplex of dimension D, a simplex of dimension D here, and to return a simplex of dimension D. So it's a factorize means that you take, so if I take one simplex composed of 1 of k, another 1, then I'm simply taking the operatic composition on each component of the permutations. So this is an operad, and you can easily check that this operad is infinity. So it's the standard result about the homogeneous bar construction of the symmetry group. This space WR is contractible as a simplicial set. Okay, and so this implies that W is an instance of E infinity operad, so it's an operad. So you can connect this operad to COM. Okay, so you have E infinity, this operad W. At least if you take valorization of whatever, it's equivalent to a part of commutative monoids, which is itself equivalent to the part of infinite dimensional little disk. Okay. So the only point in this chain is that the intermediate object is not sigma cofavant, but you can arrange it. Okay, and so, and moreover, we have an analog of James' theorem for this construction. If you take the free symmetric algebra generated by this free W algebra generated by a space X, then you get a model for omega infinity, sigma infinity X.
Sorry, the first arrow from W to COM, what is it?
It's just each space is contractible, so this means that
Oh, you see.
in each derivative you take the constant map to the base point.
Oh,
Yes. So contractible means that this map is very equivalent. Okay. So and so that's okay. So now I'm going to explain a statement by Jeffrey Smith and Clemens Berger, which says that so this is for n equals infinity, and you can refine this statement to also get the intermediate terms of the little cubes filtration. So it says that this operad W has a filtration by sub-operad, which I will denote by Wn. So W1 is quite simple. This is just the zeroth skeleton of this operad in simplicial set. It's the same as the operad of associative monoids. Okay? And so, but the other terms are more complicated. So we have this kind of nested sequence of operad in simplicial sets. And the actual statement is that this sequence of operad in simplicial sets, if you take the topological realization, then it's equivalent as a nested sequence of operad in spaces to the sequence of a little disk operad. So this means that each Wn is En in the sense which I define, and you can also construct a chain of operad equivalencies that commutes with such embeddings. Okay?
But W is not the skeleton.
No,
It's
Wn
not a
is
skeleton.
not a skeleton. So I'm going to explain. So it's constructed from a skeleton, and actually the construction of Wn is very natural. But, yeah. And so next point is that you have also an analog of James' theorem for this combinatorial operad. So this construction gives a combinatorial model of omega and sigma n. Okay. So what I need to do is to explain the construction of this Wn. So it's defined quite explicitly. Maybe what I can say for the moment is that in RET2, this construction comes from a skeleton filtration of the infinite dimensional sphere. Okay? Maybe, but first I will give the rough definition, the combinatorial definition, the explicit. I will explain this definition afterwards. Okay? So W is supposed to be a permutation for the moment. I denote by W restricted to Yj the permutation of a pair, which is defined by this process. So the best is to give an example. For instance, if I take this permutation, I restrict to 2, then I get a permutation of 1, 2, which is just obtained by removing 3 from the sequence. Okay, so it's just the transposite of 1, 2. I look at restriction to 2, 3, and I just remove 1. Okay, and I get this permutation of 2, 3. if I look at the restriction of this permutation at 1, 3, then I remove 2, and I get 1, 3. So, and this simplicial set, so W and R, consists of simplices of permutation which satisfy this variation condition. So that's again to give an example. I will start I've prepared an example in principle. 1, 2, 3. 2 and 3 to see some non-trivial things happen. So if I take the restriction of this simplex at 1, 2, then I get the sequence 1, 2, 1, 2, and 2, 1. So you see I have only one variation. Okay. If I look at the restriction of the sequence at 2, 3, I get 2, 3, 3, 2, 3, 2. So I get again one variation. If I look at the restriction of this sequence at 1, 3, and I get 1, 3, 3, 1, and 3, 2. So I get again one variation. So this implies that this simplex, so in each case you have strictly less than 2 variations, so this simplex belongs to the second layer of the filtration. Okay. So this means that so it's strictly less than what you would get from the naive skeleton filtration actually. So maybe, yeah, what I should say, that if you look at the case R equals 2, so it's very easy to check that if you, so if you look at the case R equals 2, if you look at this filtration, then you get actually the equatorial subdivision, the equatorial cell decomposition of the sphere, I don't know how to call that, maybe the Steenrod filtration. So the term W12 consists of 2 points. W22 consists of these 2 points plus 2 half circles. And W32, you have 2 hemispheres, and so on. So you can see that easily. Okay. If you look at the non-degenerate simplices. Okay. In some sense, this filtration of operads is generated by this cell decomposition, actually. Okay. I'm not going to say more, but that's the main idea. So you start with this decomposition in RET2, and you use some kind of operatic cross-section operations to generate the raw decomposition. Okay?
Yeah, but that you don't get, sorry. Here's a question. If you take those and just generate what you get by those, that's strictly smaller than these sequences. I mean, than what you get.
What do you mean? If you
you could start out with these things and start building the inside the big opera.
Yeah, okay. If you take the super opera generated by this,
yes.
I don't know what you get actually.
Yeah, is it known that that's you don't know?
Yeah, I don't know yet. So this are
so
some.
strictly smaller than the full.
It's strictly smaller, yeah, but I don't know the homotopy type of the circle. So Yeah.
Yeah, I sort of have this conjecture that it's still the same, that you could get away with these guys instead of.
Yeah, I don't. Yeah. So you see, this means that you. So it's some. So the filtration is some kind of universal if you sense that in the sense that if you look at this restriction operations, then you are looking at operatic composites with unitary operations actually. You plug units at all positions except I and J. Okay? And
Are they related somehow to brain groups?
no, not I don't think so, no. No.
Yeah, because the two algebras are somehow related.
Yeah, so this is the second talk today. Okay?
But you can see here.
No, not in this filtration. So it's I wouldn't be able to construct by hand homotopic currents between this W2 and the brighter parts. Okay.
So in a sense, they're orthogonal to the braids. Dynamic.
Okay. So and actually, so maybe a bit quicker. Not going to. So the idea is that so Clemens said, so to prove, this is the definition actually of the filtration. And to prove a statement, so there is a claim. First, if you look at the term, so if you look at the term W1, it means that you have no variation at all. So you get nothing but the zeroth skeleton of the part. So that's why you retrieve just a permutation. So degenerate simplices of permutations. Okay. And in general, so you see on this example that this is more complicated. Okay. So I will just sketch a proof of the theorem. I would like to say that the idea is to consider some kind of cell structures which is shaped on objects I call the complete graph posets, which in some sense rigidify this operads. And the main difficulty is that if you have homotopic currents made in operads 2 or EN, then you have too many homotopic currents. It's very hard to control the homotopic currents. And so the main point is that in some sense you have to add two structures in order to rigidify the operads. In this case, the structures are encoded by it's some kind of cell structures on the operads, some kind of cell decomposition. And this the graph posets are posets which give the shape of these decompositions. So it gives a rough definition. So K R is a component of this poset. So it's the set of pairs, mu, sigma. So mu is a collection of non-negative integers indexed by pairs. And sigma is a permutation. So maybe I should give a graphical picture. So actually the pairs. So you see you can identify pairs, ij, with edges of a complete graph. Whose vertices are indexed by 1R. Assuming that the ij is a pair in 1R. So this explains the name complete graph poset. So it's an example. I hope I have not forgotten any edge. And these indices can be regarded as weights which are assigned to each edge. So I take 2 for this one, 0, 0, 2, 1. Okay. So this is an element in. Yeah, okay, and I forgot the permutation. So the permutation is equivalent to an ordering of the vertices, and in general, you can materialize this ordering. So I assume that 1 is the smallest, and then I will take 2 goes to 1. I think this is okay. So you can specify an ordering by current or orientation of the edges. Okay, so this gives you an element in K4. And the claim. So this set is equipped to the partial order relation, which says that so the poset element defined by a pair, mu sigma, is less or equal than the poset element defined by mu tau. If for each ij, we have either mu ij is strictly less than mu ij, or you have an identity between the weight mu ij, the weight mu ij, and the orientation of the edge. Okay? And so now I'm going to explain in the next slide how I use that. So for instance, I'll give a simple example. So if I take 1, 2, so this element is lower than this one. Okay. And so to each simplex, W0, WD, I can associate an element in this poset. So this is pretty simple. I'm just using this construction. So I mean, mu ij is the variation number of the restriction of the sequence W0, WD to ij. And sigma is the last component of this permutation tuple. Okay, so for instance, this element here, to this element you associate, so the last permutation is, I will draw the picture. So the last permutation is 3 to 1. 3 to 1, and each weight is equal to 1, because in each case the variation number is 1. Okay? So this is natural construction. And the claim is that this WR has a cell decomposition where each cell, W kappa, is the set. So in dimension D, the set of D plus 1 tuple of permutations of which associated poset element is lower than kappa. Okay. And in some sense, so this cell decomposition refines the filtration. I mean, if you take some restriction of a union, okay, then I get exactly Wn, where in Kn, I'm assuming Kn consists of the subposet of pairs. Okay. Mu sigma such that each weight is strictly less than n. Okay. So if you take a union over this subposet of H system, of a complete graph poset elements, then you get exactly the nth layer of the filtration of the baratical subpath. And the idea is to use this structure to prove the existence of the unique occurrences connected with Wn to the little disk. Okay. So we have first observation. So 1 point. Yeah. Okay. I have to explain that the complete graph poset also inherits an operads structure. Okay. Which models the image of cells under the composition operations attached to the baratical subpath. So this means the following. So first, if you look at the action of a permutation of S in sigma R and WR, then you see that the action of this permutation then maps the cell WK to the cell WSK for some poset element SK associated to K. So, okay, so this gives the action of S on the poset. And you have a similar picture for the operatic composition operations. Okay, so the composition, the operatic composition maps a Cartesian product of cells to another cell, which is associated to an element in the complete graph posets, which represent an operatic composition of these elements alpha and beta. Okay, it's actually very easy to make things explicit. So just yeah, I'll go on. So just to say how we use that. So first lemma, each simplicial set, each cell is contractible. So I mean, the claim is that you actually get a genuine cell structure, which means that the cells are contractible, at least, okay, not necessarily homomorphic to disk. The interiors of a cell is not necessarily empty, but at least you have this property. And also the diagram is nice enough, means it's a coherent diagram with respect to some model structure. Which means that if you take a union of cells, so it implies things like if you take the intersection of cells intersects on subcells and so on. Okay. And so these two statements imply that this is really a rigid structure. So it says that if you have this kind of things, this implies that W and at least each Wn Wn can be obtained is equivalent to the nerve of the poset. Okay, you can reconstruct Wn from the simplicial construction of the poset. Okay, and so to prove
Is that the complete set of conditions you require? I thought you required a bit more.
sorry?
But you've just got two conditions there. You
Yeah,
can that Wn is homotopy equivalent to the nerve of the Kn.
Yeah.
You need more conditions.
No, I think just that. So each, yeah, if you, yeah. So if this object forms a diagram, okay, and so I've not been explicit about the second condition. So as soon as you have already coherent diagram.
I see. What you haven't explained is what you mean by a coherent diagram.
Yeah, coherent is not. I'm not really complete. So you need more actually. It's,
yeah.
you need very. Yeah.
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 Okay.
Yeah. So there is a, yeah, I mean you have two general conditions like this, which ensure that you get such a result, okay? And so to establish that Wn is equivalent to Dn, what you would check is that the operand of little disk, D infinity, has a similar cell structure. So it's not for the same poset, you have to change because you cannot realize this condition with the poset kappa, with the poset K, the complete graph poset. You have to change the poset slightly. At least you have, I think you keep this condition, but this one fails. So you have to change things, it's complicated. But you can check that the modified poset, K prime, is homotopical to K, in the sense that you have this relation. And you have also something similar, lemma, which says that if you look at Dn, the topological relation of K prime n. Okay. So now you see to check that Wn is equivalent to Dn as an operand, then you use this equivalence at the poset level. Okay. So, okay. Yeah. So maybe, yeah, I will finish. So just to say, just to announce what I wanted to say after that, but I'll go to other things in the second talk. So I wanted to go back to the surjection operand, which John explained in his talk. I wanted to, so if you recognize, so this is the operand of surjection satisfying these non-degeneracy conditions. And what we claim, actually, Berger and me, is that this operad comes from some kind of prismatic decomposition of WR. It's related to the Baratekos operad somehow. And prismatic means so to any surjection, you can associate a prism like that. And you can deduce all properties of this surjection operad from the Baratekos operad, actually. Okay. And there is another statement, so I just said in the introduction, that in some sense, the last point, the Yen operad, so yeah. So Bruno explained, that Gershnaber operad is Kosul, and this, so you have more actually, you can assemble the Kosul duality equivalence into diagrams. And what I claim is that you have equivalencies defined at the level of a chain operads of little disk of the Baratekos operad, the filtration of the Baratekos operad, which realizes this Kosul duality equivalence. There's still a conjecture that what you have at the chain level is still holds at the topological level in some sense. So this conjecture would have significant applications in the Grothendieck calculus. Actually, it's a project of Michael Chin. Okay, so that's all for the first part. So yeah.
Can you distribute these slides?
Which one? Sorry?
Is it available?
Can you put them online?
Yeah,
Give them
sure.
to me and we put it on the web page of the program.
Okay.
Sure.
Sure.
Because we heard only 1/3 of the talk.
Or more.
So I have a question. This recognition theorem, it depends on you knowing what's happening at the two space, doesn't it?
Yeah, exactly.
It depends on you knowing that you've got something S infinity with
Exactly.
this particular.
Yeah, you start with the Stewart cell decomposition of S infinity. Yes.
Is there a version of the recognition theorem which doesn't assume that?
No, I don't know. I'm not aware of any statement like that. Yeah. Maybe, yeah.
This needs because sort of topologically you want a higher cup P product, so you always need.
Yeah, but you could take a subdivision of this.
You could take a subdivision.
Of this cell
I would
decomposition.
make smaller, sure.
I don't know any.
Make it bigger.
Yeah, sorry.
I don't know any example where
In a
this.
sense, it almost feels like what you're doing. What you're doing is saying, this is the minimal thing
Yeah,
that
exactly.
can work, right?
Exactly. Yeah.
Right.
Yeah.
But I
Exactly.
mean, can you make a statement which doesn't have something minimal there?
Yeah, maybe. Yeah, but I don't know any example. So yeah, maybe.
Yeah, I do actually.
Ah, okay.
Which is why I'm asking.
Yeah. Okay. Yeah.
Another question? Let's make a break.
Yeah.
Resume it was in 30 minutes. What did we say? In 30 minutes? No, we said.
Yeah, at 3:45 or yeah.
Perfect. 2 to 4.